people. Application of your compound bar and inducement or temperature inducement stresses. Okay, let us do that application. Okay, we are given equation here. We are given equation. A compound bar consists of rod with a cross-sectional area. We are given the copper and its cross-sectional area. It is 500. It's a solid one, right? Then we are given the steel pipe with the cross-sectional area. Its cross-sectional area it is 700. Rod fits inside the pipe. Both are initially, this is their length, L1 equals to L2, with their ends rigidly fixed together. Now, you are dealing with compounded bars, and in this case, the solid one fits inside the pipe. The solid, it is your copper, then the pipe, it is your steel. Okay, now this is your parallel connection. You can tell. Now, we are as well given the Young modulus for steel, Young modulus for copper, coefficient of expansions. We are given for both materials. Now, calculate the following. The magnitude, they want us to calculate the magnitude of the magnitude and the nature of stresses, the magnitude of your stress, and determine its nature of the stress induced in the copper and steel if the temperature increases by. Now let's make this point. If you are given the statement like this, increases by or rises by, then you know that the given temperature, it is the byproduct, it is the change in temperature. There's no need for you to calculate it. At times they will trick you. You will be given the T1, but as they continue with the given statement, then they would say the temperature rises by. Then you know that the rises by, it is the change in temperature. Whether you are given the T1 or whatsoever, it doesn't matter. You need to stick to the given principle and the indications. Rises by, increases by, it's a byproduct, it is the change in temperature. There's no need for us to calculate it. In calculating it, we're going to use, if they said temperature increases from 2, then it was going to be T2 minus T1. Okay, but at times you will be given T1 and you will be given the byproduct. Don't take the byproduct to be the T2 and you want to minus it from, you want to minus T1 from. No. Read the statement carefully. So we are given the change in temperature. Now, the fact that it is the parallel connection, this is the formula that we will be using. F, we need to first determine the force for us to be able to calculate the magnitude of the stress and determine the nature of that stress. But we first have to calculate the stress that occurs as a result of the temperature increase. Okay, now we are having force. This is the formula. Area of your steel, Young modulus steel, plus 1 over area copper, Young modulus copper, close bracket, equals to change in temperature, coefficient of copper minus the coefficient of steel. Now, this is the formula for parallel connection. This is the formula that we'll be using to calculate for your force. And this force, it's a common force for both materials. That is the force that we'll be using to calculate the stresses, okay? Force equals to 1 over. We are given the steel as 700 times 10 to the power negative 6, since well it is millimil squared, multiplied by 210 times 10 to the power 9, plus 1 over 500 multiplied by 10 to the power negative 6 multiplied by 105 times 10 to the power 9, close bracket, equals to 75. 18 minus 12 multiplied by 10 to the power negative 6. Right. This, after substituting the given information into the formula, we can then calculate the F. Therefore, force would be, now when we minus 12 from 18, we get 6. to 6 times 10 to the power negative 6 multiplied by 75. Then I got my answer as 4,5 times 10 to the power negative 4. Then in removing this bracket here, when I multiply and divide and add, then I got my answer as 1,905 times 10 to the power negative 8. Then I got my answer as 23,619,095 Newton. Okay, then this is the force that we'll be using to calculate our stresses. Stress copper equals to the force. What is the force? The one that we've calculated, it is 23,619,095 divided by the area copper, it is 700 times 10 to the power negative 6. Then I got a copper, it is 5. It is 500. This one is for steel. Okay, we are calculating the stress for steel. Then we got 33. I got 33,742 megapascal. Then the stress for copper would be 23,619,095 divided by 500 times 10 to the power negative 6. Then I got my answer as 47,238 megapascal. Now, this is how you calculate your stresses. We've managed to calculate our stresses. Now, in determining the nature, let me give you the picture of determining the nature. You are having the transference of energy in this parallel connection. This is your copper. Copper, it is of weaker material comparing to your steel. Now, the one that will react quicker comparing to the two material, it is copper. Copper will expand quicker. Okay, then steel will expand slowly, and steel will become a benchmark for change in length. Now, steel will expand to this level. That level of a harder material will be the benchmark of change in length. Okay, now the fact that steel was pulling away from the object, it means the force that it is being applied under your steel, it is the force tensile. It means the stress that we will get as a result of the force tensile, it is what? Stress tensile. It means the steel here, it's experiencing what? Tensile. The nature of your steel there, it is what? Tensile. Then when coming to copper, the fact that copper has expanded quicker, and this is the benchmark, it is as if steel is dragging back copper to its level where it is. Now, as steel is pulling back the copper to its level, you can see that copper is now converging towards, it's heading towards the object or the material or the body of the object itself. It then means the force that it is being experienced under under your copper, it is what? Force compression. It then means this the stress that will be experienced there, it is the force compression. That would be the nature on the copper. Now we've managed to determine the nature of the stresses here. Your steel, it is your tensile. We're experiencing the tensile. Okay, then the copper, it is the compression. Now, based on your book, it indicates that tensile, it is the plus. Then compression, it is the minus. Okay, we've managed to determine the nature of your stresses. Okay, this is how you tackle this question. Let's go to the second question. It is the follow-up to this question there. Okay, now they want us now to calculate the resultant stresses caused by the increase in temperature given in A and the application. Now, for us to be able to calculate, we've already calculated the stresses as a result of the increase in temperature. Now we need to calculate the stresses as a result of the force applied. And the force that it is being applied is the force tensile. That means you are having your material, then you are having the force tensile applied, force tensile. That means the stresses that we will be experiencing here, it is the stress tensile. This one, it is easy, straight to the point. It means both material that will experience what? stress tensile. But don't forget that still it is the benchmark of what? Of the change in length. Steel, if steel extends to this point, copper will as well be pulled to that point. Because steel, it is of a harder material, it now becomes the benchmark for change in length. Okay. Now, the force that is being applied, it is 40 kilonewtons. What is it that we know about the parallel? We know that length steel equals to length copper. The change in length under your steel equals to the change in length under the copper. Then the force applied, because of they are of different material. Copper, well, it is of weaker material, steel, it is of hard material. We then have to determine from the applied force uh, if what amount of force will copper absorb, what amount of force from the 40 kilo will copper absorb, and the steel as well. Okay, what do I mean by that? Giving you that funny explanation of how much will copper absorb. Okay, let's give you the picture. If this 40 kilonewton is being applied here, you would realize, let's say we start with steel. We start with steel. The force is being applied under that steel. We realize that when the force it is somewhere here 32 kilonewton, then steel started to do what? To deform. Okay. Now, the very same force it's been applied under your copper. Then we realize that when the force was somewhere there on 8 kilonewton, then copper started to deform. You can tell that the Young modulus, the strength of material, it is not what the same. Now, out of 40 kilonewton that it is being applied under on this material, copper was able to absorb 8 kilonewton. Then steel was able to absorb what? 32 kilonewton. When you add the two, you must still get what? 40 kilonewton. That's what I mean by that funny explanation that I just gave you now. Okay. Then we know that total. Therefore, it will be force copper plus force steel. Because when you add 8 and 32, you must get what? 40. That is why we are having this formula to calculate the force total under your parallel connection. And under the parallel connection, out of this 40, how much of that 40 will copper absorb? How much of that 40 will steel absorb? Okay. Hence, we are using this formula. Now, we know again in calculating the stress, it is force over area. Then force would be stress over area. Now, the fact that we are determining the stresses, we don't know the force, the amount of force that will be absorbed by copper if 40 has been applied. Hence, we will then convert everything and apply what? Apply this formula in calculating whatever that they want us to apply. If we knew the forces, we're then going to apply this force direct, but we don't know. Hence, we will then convert, manipulate the new formula. Now, we are having 40 times 10 to the power 3 equals to F equals to stress copper area copper plus stress steel area steel. Then we are having our area copper, it is 500 times 10 to the power negative 6 multiplied by stress copper plus 700 times 10 to the power negative 6 multiplied by stress steel. We'll denote this our equation 1. Right. Then the change, let's look at the change. The change, we know that it is stress steel over Young modulus steel equals to stress copper over Young modulus copper. Remember, the L and the L, they are of the same, then they will cancel out. This formula, it is taken from that formula, FL over AE equals to FL over AE. Now, this formula, it is applicable only if we know the forces. Can then use this formula. But the fact that we don't know the forces, then hence we will convert force over area. Force over area, it is stress. Force over area, it is what? It is stress. The length and the length will cancel out. Then we'll have what? Stress over E, stress over E. That's what we have there. We are having stress steel, stress copper over Young modulus copper. Then we make steel the subject of the formula. Then it will be stress copper multiplied by E steel over Young modulus copper. Having stress copper Young modulus, it is 210 divide by 105. Gigapascal will cancel out. Then we get our stress steel as 2 times stress copper 2. Then we will then substitute equation 2 into equation 1. Now, when we substitute equation 2 into equation 1, where there's stress steel, we'll substitute it with what? 2 times stress copper, of which we are having 40 by 10 to the equals to 500 times 10 to 6 multiplied by stress copper plus 700 times 10 to the power negative 6 multiplied by 2 times stress copper. Then we get our answer as stress copper. You can then manipulate and make stress copper the subject of the formula. When you multiply 700 times 2, 700. When you multiply, did I do the right? Yes, 700. This one was the 700. Now, when you multiply, let's see, what did I do here? Okay, let's multiply here. 2 times 700 times 10 to the power negative 6 plus 500 times 10 to the power negative 6. Right. Okay. Then you are having 40 times 10 to the power 3 divide by the answer that we got. Right. Divide by 1, 2, 3, 4, 5, 6. Okay. Now I get my stress copper. As 21. I get my stress copper as 21. I've already calculated everything there. Stress copper is 21,052. Okay, that's what I got. Then our stress steel would be 2 times 21,052. Then you get your stress steel multiplied by 2. Then you get your answer as 42. Now our stress steel, it is what? 42,105 megapascal. Right. This is how you tackle this question. Okay, let's look at the third question here. The third question, I will leave it to you to attempt it, to solve it. Now, we said it that L final equals to LO plus the change in length. Now, what is it that we know about the change in length? We know that LS equals to change in length C. It means here we are having L final equals to LO plus change in length S or change in length C. This is how you tackle the last question in calculating what? The L final. Okay, apply this in calculating the L final, good people. Apply this in calculating the L final there. Or change in length equals to LO coefficient multiplied by the byproduct there. This formula as well, it is still applicable because the change in LS equals to the change in LC. It is still applicable as well in getting the required answer there. Okay, I will leave it to you to attempt it, this one. Okay, let's move on to the second question. Second question, a compound bar consists of a solid steel rod inside a copper tube. Inside the copper tube, it is similar to the one that we did. It is similar. You are having this copper tube solid and the pipe. That's exactly what we have. Then we need to establish which one it is solid, which one it is not. A copper bar consists of a solid steel. It means inside here we are having the steel. Then a rod inside a tube, a copper. Then this one would be the tube. Would be the tube. Okay, the copper would be the tube. This is what we have there. Ends richly fixed together. The steel rod has a cross-sectional area. This is the area for steel. Then this is the area for copper, steel. Then check the wording here. They want us to calculate the magnitude of nature of stresses in the copper and steel if the temperature is reduced from. Now you are having this from 2. Okay, you are having this from 2. Now be careful. Be careful. From, this is T1. 2, this is T2. Now when you deal with these questions, it is very empirical to read the questions clearly. So it is from 2. That means in calculating the change in temperature, you are having 25 minus 95, of which the answer here would be minus 70 degrees Celsius. Because it was clear that they said from 2. From 2 is reduced from 2, T1 to T2. Okay. Now we are given the Young modulus for steel, Young modulus for copper. We are given the coefficient of expansion. There they are. Now they want us to then calculate the magnitude and the nature of stresses in the copper and steel. Now can we then do that? Let's do that, good people. Okay. The fact that it is connected in parallel, this is what we have. It will be 1 over, what is our area? What is our area? We are having 350 multiply by 10 to the power negative 6 multiply by the steel. This is this of steel times 10 to the power 9 plus 1 over 854. 854 times 10 to the power negative 6 multiplied by 100 times 10 to the power negative times 10 to the power 9 equals to the change in temperature. Don't forget, equals to negative 17, 18 minus 12 times 10 to the power negative 6. Now, when coming to this one, like I'm saying, you need to be careful. Okay, you need to be careful. Negative multiplied by positive would be negative, multiplied by that would be positive. Now we are having 18, negative 18. We are having negative 18 plus 12. Yeah, because you are having, if we were to remove the bracket, we are having 6 times 10 to the 6 times 10 to the power negative 6, right, multiplied by negative 70, right. Now, yes, now let's go ahead and solve this mystery of ours. Okay, let's solve this mystery of ours. This is what we have here. Force, open bracket. After we've removed the brackets, we will land ourselves with 2,5995 times 10 to the power negative 8 equals to, okay, equals to negative. It will be negative 4,0 comma 2 times 10 to the power negative 4. Okay, then our force would be negative 4 comma 2 times 10 to the power negative 4 divided by 2,5995 times 10 to the power negative 8. Then we get our force there as negative 1,615 comma 953 Newton. Okay, this is what we got here as our force. Now this is the force that we'll be using to calculate whatever that they want us to calculate, good people. Okay, now we know that we don't have a negative force. Okay, we know that we don't have a negative force. We said it. It means the force here, this force that it is being applied, this force here that it is being applied here based on this would be the nature of the force being applied. It means it is compression. It is the force compression. Okay, it is the force compression. Now we've managed. They said on the given statement here. Did they indicate? Yes, they did indicate. And an axial compressive load of, it is 50 kilonewton. Okay, the force that is being applied, it is compressive. It's a compressive force. That means the force under the inducement there, it is not the tensile, but it is what? Compressive. Okay, it's not. All right. Now the force here under the change in temperature, it is the compressive force. We can then calculate the stresses. We are having the stress copper equals to 16156,953 divided by the area copper, it is 854 times 10 to the power negative 6. Then we get our where's my eye cursor now? Negative 6. Now we get our answer as 18 comma 919 megapascal. Okay, then stress steel, we get our stress steel, it will be 16156,953 divided by 85, not 85, I mean to say, it is 350 times 10 to the power negative 6. Then I get my stress as 46,163 megapascal. We know from here that the forces, now check this, the steel, it's experiencing the force compression. That means the stress here, it is compression. Okay, steel is experiencing compression because it's going inside. All right, then steel, it becomes a benchmark. Copper, it is of weaker material, it will go all the way, but steel has to pull copper back to its level. When it pulls copper to its level, now copper, it is the force that it is moving away from. It means here the copper, it is experiencing the tensile, but the steel, it's experiencing compression. It means copper here, it is plus, then the steel, it is minus. Please make note. Okay, then the second question that they wanted us to calculate, it is the resultant. We are given the compressive force of 50 kilonewton there. Okay, now we are having Ft equals to force total or force compression equals to force steel plus force copper. Then we know that we are having stress steel, area steel plus stress copper, area copper. Then we are having 50 times 10 to the power 3. Then our area for steel, okay, then the area for steel, it is 350 times 10 to the power negative 6. Area steel plus 854 times 10 to the power negative 6. Area copper. This would be our formula number 1. Then we know that the change in steel equals to the change in copper. By now we know. Then we are having stress steel over Young modulus steel equals to stress copper over Young modulus copper. Then we make steel the subject of the formula. Copper, stress copper, E steel over E compressive. Then we are having 200 Young modulus of gigapascal. Stress steel over 100 gigapascal. Then the gigapascal will cancel out the zeros and the zeros will cancel out. Then we'll have 2 stress copper. This would be our equation 2. Then we'll substitute equation 2 into first equation. Then when we substitute that into the first equation, then we will have, here we didn't substitute with our, we did. This is stress. These are your stresses, okay. Then we will have 500, to say times 10 to the power 3 equals to 350. It will be 350 times 10 to the power negative 6. Where there's a steel, we'll substitute it with what? Times 2 times copper plus 854 times 10 to the power negative 6 multiplied by stress copper. Then we lend ourselves, good people, we will lend ourselves with 50 times 10 to the power 3 equals to 554 times 10 to the power negative 3 multiplied by copper. Then copper would be 50 times 10 to the power 3. This is 50, please. It's not 8. Divide by 1,554 times 10 to the power negative 3. Then I get my stress as. Then I got my stress on the copper as 32,175 megapascal. Then when we substitute this answer into stress steel equals to 2 times 32,175, then I get my answer as 64,33 megapascal. Is it 35 megapascal? Please verify with me there. Now, this is what we got as our answer on the stresses. The stresses, the nature of stresses here. The nature of stresses there, good people, please don't make a mistake. The nature of stresses under the axial load, it is force compression. It means the stresses here, because of the force applied, we are having compression. And what is it that we know about compression? Minus. Okay. Now, in calculating the resultant, can I wipe so that I can use the smaller space here? In calculating the resultant, I want us to calculate the resultant. Okay. Now let me wipe here. Let me wipe this part. You already have this part. We already have that part. Tensile. Now, we remember the force under your inducement. The force under your inducement, okay? The first part under your inducement, we had the stress still as 46,163 megapascal. Then we had stress copper as, what is it? Am I still? We had the stress there as 18,919 megapascal. And we said under this, we said the steel, it's experiencing compression. This is the compression. Then we said copper, it will experience tensile. Okay, that's what we said. Now, based on what we have determined here as the nature of, and we know that compression, it is minus and that it is plus. Now, in calculating the resultant, we'll start with that of steel. Okay, we are having 46, it's a minus, comma 163, okay, minus 64,35. Then we get our answer. Let's add them. I didn't add them, those ones. Okay, it is 46,163 plus 64,35. Okay, I'll take 35 there, but verify for me, please. Then I get my answer is 110. 110,513 megapascal. And this is what compression, its nature. Then we come under your total resultant stress under your copper. We are having under your copper, we are having 32 minus 32,175 plus 18,919. Then we get our answer as, then our answer would be 32,175 minus 18,919. Then I get my answer is 12 there. I got my answer is 12,259. What's my case? Did I? Yes. Oh, I said 32. 31. Why did I put as 31? Negative 32,175 plus 18,919. Right. I get my answer is 13. Not, where's my writing tool now? Oh, God. Yes. I get my answer is 13, it's a negative 1, 256. It's a negative 1. Okay. It's a negative 1. Here we got negative, negative. Negative, when we added them, we got the answer obviously as negative 110. And we said it that negative, it's a compression. Okay. Then here we are having negative 32 plus, then we got the answer is negative there. All right. It then means here as well, it is what? Compression. Boom. This is how you tackle this equation. Now, based on your books, this was activity, this was summative number 5. Okay, summative number 5, please verify it with me and check if we got the correct answers or not. It was number 5 and summative number 3. It was number 5 there. It was number 5. Yes. The answer is compression, compression. Check for me and verify with me, but this is how we tackle these questions, good people. Thank you, good people. No, man, it was something else, eh? Ngikhaleke stopile mas.